I would request everyone to take their seats. We will begin in just about a minute. Good evening, everyone. Well, good afternoon, good evening. And we will begin now. I know we have a few strays walking in. I would request whoever's outside to please bring their cup of tea inside. Good afternoon, everyone. I'm Bhavna Mehra, the Vice President of the Infosys Science Foundation. Together with my team, Swati Revankar, Sireen Qasim, and Shruti Sharikumar, I welcome you here to the 5th edition of the Infosys Prize Winners Symposium. This symposium has held space for curiosity beyond your own fields, and we request the winners of the prize to speak for around 13 to 14 minutes, with 5 minutes of Q&A time from you, the audience. This may seem brief, but you can always grab a cup of tea later and badger them. On that note, let's begin. I invite Professor Nikhil Agarwal, our winner of the Infosys Prize in Economics. Yeah, that one is.
Thank you so much. It's really an honor to speak here. I want to share some of the work that I've been doing with my collaborators, most notably Paulo Someni and Itai Ashlagi. And this work is really thinking about how to use data to engineer real-world institutions. And so the field of economics that you might associate me with is known as market design. So the traditional textbook view of how a market works is via this Marshallian cross that many of you might be familiar with. There's a demand curve, there's a supply curve, and somehow they intersect. There's a price, and there's a equilibrium quantity. The market clears very well. But if you think about a real-world market, any that you have participated in, there are specific norms, rules, potentially frictions, and you don't necessarily see this Marshallian cross. Okay? So the real institutions matter. So for example, at MIT, we do not raise the tuition so that demand exactly equals supply. Okay? In many other markets, prices are not even allowed. For example, kidneys, which I'm going to talk about, should not be auctioned. So market design studies real-world institutions and the details about how they truly perform. And I specifically work on empirical market design, which is a data-driven approach to thinking about market design. And there are 3 core goals of this field. The first is to diagnose market failures. So when you see an institution that may not be working well, why is it not working well? Is it market power? Is it some kind of bad rules, some frictions that are happening, information frictions, maybe search frictions? And then we'll try to think about how you might try to resolve those issues. You'll think about potentially a couple of different designs, maybe an auction, maybe something else. And we will, in my area, we will try to quantify the trade-offs between these designs. And I'll give you some concrete examples in a bit. How much is one set of rules better than another set of rules? And this type of knowledge combined with practical interaction with real-world practitioners, will allow us to propose new designs. And that will allow us to potentially engineer better solutions and better institutions to potentially fix the problem that we find. So as opposed to keeping this at a very high level, let me give you a specific type of problem that I've been working on. It's about a third of my research portfolio. It's a kidney allocation problem. Okay? So it's a high-stakes rationing problem. In the United States, more than 100,000 patients are currently waiting for a life-saving kidney transplant. In India, we do not have such good estimates of exactly what the waitlist size is. Some estimates are above 200,000, some estimates are close to 500,000. And India happens to be, unfortunately, at the very low end of the number of kidney transplants per million population. You can see India on the extreme right, the sixth lowest in this graph, and the United States is the most. And in India, most of the transplants come through living donor transplants. So most of us in this room have 2 kidneys. We can, if you're healthy enough, donate one of these kidneys and not have a substantial impact on your health. You can also get kidneys from deceased donors. These are people who pass away and then are willing to donate one of their kidneys, or their family does so. So how do you design the waitlist priority rules? Because we shouldn't auction kidneys. That seems an unethical thing. In most countries, except Iran, does not have prices, at least legal market for kidneys. There's efficiency considerations, there are fairness issues, and you want to minimize kidney waste. And how can we increase the number of transplants that are conducted, perhaps, without using money? Okay? So a very important idea is a kidney exchange, a type of exchange called a kidney exchange. Here I have a simple example. Imagine that there are 2 patient donor pairs. Maybe somebody I love needs a kidney, and I'm willing to donate one of my kidneys, but it so happens that my kidney is not compatible because of blood type issues or tissue type incompatibility issues. Maybe somebody else is in a similar situation. A solution would be that I donate my kidney to that potential recipient, and their intended donor donates a kidney to my intended recipient. In this way, both patients get a transplant, no money was exchanged, so we didn't auction any organs, and that seems like a good solution, if possible, and to create more transplants. This is the simplest example. There are 3-way swaps. There are chains that are initiated by people who donate a kidney to an anonymous person who they do not know. And this foundational work was recognized by the Nobel Prize Committee in 2012 in a prize to Alvin Roth, who was one of my advisors. This idea has taken off in many different countries. In India, it's starting to grow. There is the Trivedi Institute of Transplantation Sciences in Ahmedabad that conducted 539 kidney exchanges in the last 2 decades. So those ideas were based on theoretical approaches, and the idea really is that if you have all, say, the potential donors who are willing to give up their kidneys for an intended recipient, and all the patients in one giant platform, then what we could do is we could find the maximal match. We could make the maximum number of transplants and make it happen. So the vision was that there's going to be one large system. Unfortunately, we looked at the data, some of my collaborators and I, in a paper that was published in 2019, and we found that instead of there being one large platform in the United States that is doing most of the transplantations, there are little islands where a hospital like the Trivedi Institute is doing its own set of transplantations, another hospital is doing its own set of transplantations. When they're doing it, they're trying to arrange matches between a smaller set of patients and donors, and they don't know what another hospital might have. And so there are some potential matches that don't get realized because maybe there was a cross-hospital match that doesn't occur. Okay, so we found that problem, and we tried to think about how important that problem is, quantify it, and then see if there's a solution to it. So on the graph here, I've got, on the horizontal axis, number of donors submitted per year. Think about that as how thick the market is, how many patients and donors are there on a platform like a hospital or something else. And on the vertical axis is the proportion of donors that would get transplanted, or proportion of total number of transplants that would happen per donor. And you see this graph that shows that if you're a very small platform, very few donors get transplanted, but then it plateaus out and the matching is more efficient. So there are some gains to having this large scale, but they plateau out to some point. The blue vertical line shows the largest kidney exchange platform in the United States. The gray histogram, which has the right axis, shows you the distribution of hospital sizes in the United States. So most transplants are happening at a very small scale, and they could be made more efficient. Okay? So the diagnosis of the market failure here was that there isn't enough thickness. There isn't enough participation on these main platforms. How do you fix this market failure? So we proposed a two-pronged approach. The first one is that we saw signs in the data that there are financial disincentives from participating in the platform fully. Small hospitals that could only do a few transplantations were not participating in the platform. There's some fees that seem pretty high per transplant for these small hospitals. And reimbursing those costs would actually save the US government money because it would otherwise pay for kidney dialysis care. The second thing that we found was that the design of the platforms itself was inefficient. So the design was more or less a linear program that would maximize the number of transplantations. That seems interesting, but think about a hospital, and you're a surgeon, you're taking care of some patients and donors. You could transplant them within your hospital. Okay? Now you propose that these patients and donors register on this national platform. You don't know whether your patients and donors are going to get transplanted. In some cases, they won't. Okay? And so if you're acting in the best interest of your own patients and donors, you may do the matches that you see within the hospital and send the rest to the platform. And that turns out to be inefficient because we don't see all the potential patients and donors at the same time. Okay, so that creates a disincentive for participation, and so we created a data-driven design that encouraged hospital participation that tuned the match priorities to undo this disincentive. Okay? And the principle of this second design was adopted by the two largest kidney exchange platforms in the United States in the recent years. And so instead of the current state or the old state being more that all these little dots that are individual hospitals doing their own matching, we can create a dense, larger network in which we can find more matches. Most of the transplants that happen in the United States do not come from living donors, however. Most of them come from deceased donors. So I also studied the deceased donor organ wait list in a couple of papers. A surprising fact that will convince you that the organ donor list is not designed efficiently is that 20% of medically suitable kidneys that are recovered from deceased donors are discarded. These are kidneys that countries like France would have, in many cases, transplanted. Okay? So what's going on? Well, when a donor whose family is willing to donate a kidney, perhaps, has their organs made available, then there is a priority list that's drawn up based on the characteristics of patients who need a transplant and their waiting time. These organs are then offered in that priority order. Patients are given the opportunity in consultation with their doctors to either accept or deny this organ offer, and when they do that, they take some time. This time accumulates, and before you know it, maybe the kidney is no longer viable for transplantation. And so we need to create a dynamic rationing design system that thinks about how patients on this waitlist should be prioritized in order to maximize the use of these organs, reduce wastage, but also find good matches. Perhaps if you are going to benefit more from a particular kidney than I would, and both of us are on the list, maybe you should get it and not me. But there are also ethical and fairness considerations here in terms of who gets transplanted. So here, what we did was we set up, using the data, we set up and estimated the parameters of a dynamic choice model for the patient-surgeon behavior. So you imagine you're on the waitlist queue. If you get offered a match, offered a kidney, you might accept or reject it. If you reject it, it's offered to the next patient on the queue. Okay, so you still hold the priority line, so you make a dynamic decision. If you accept it, the transplant occurs, and maybe their life is from transplantation. So there are two components to a simulation model. The first is a dynamic choice model that models how patients and surgeons would behave in any given system. And the second is an estimate that says, how long would you live if you were given this kidney, or versus how long would I live? Now, we cannot do randomized controlled trials where we say, you randomly get a kidney and I don't randomly get a kidney. Okay, so you need to create as-if random assignment. And for that, we use quasi-experimental methods because just by chance, maybe you get the offer, then I don't. And we can see those kinds of experiments in the world, and we can estimate the survival benefits of various kidneys. So what came out of this? there are two types of gains that came out of it, and one trade-off and two types of gains. So if you take a mechanism that tailors offer rates based on detailed patient and donor characteristics, you could think about either increasing the patient welfare in terms of equivalent donor supply or the reduction in kidney fraction discarded. We found approximately optimal priority system that produces better matches and reduces discards, which leads to shorter waitlist queues. A second thing that we found is that using our life years model, that as opposed to the observed assignment that produces 9.29 years of life, additional life for the average transplanted patient, we can create a system that produces 11 years of life for the average patient. But this has a drawback. This would require transplanting younger and otherwise healthier patients. So there's a trade-off, there's a planner's dilemma between transplanting sick versus maximizing life years. And this idea of empirical market design has been applied by me and my collaborators and my students more broadly. I've studied education, labor markets, that's where I got my start. And then now I'm thinking about designing human AI collaboration in radiology, where we had a large experiment. So I just want to conclude by saying that this way of thinking about problems turns an economist into an engineer. Just as an engineer relies on theory, data, and simulations and practical experience to design a bridge, the goal of a market designer is to take what they've learned from the various academic disciplines, but also from the real world, to remedy a market failure, and so an economist becomes an engineer. I'm looking forward to your comments and any questions that you might have.
If you have a question, please raise your hand and we'll pass a mic to you.
I have a question. Does your model of a wider distribution of hubs in this network rest on the assumption that all transplant locations have equally favorable outcomes for the surgical procedure? What I've heard is that those institutions that do a much larger number of a particular operation generally have a higher success rate. So people would like to favor those kinds of institutions rather than just being assigned on the basis of this distribution.
Yeah. So there are two parts to your question. So the first part is, where does the patient get transplanted? And our simulation methods keep fixed where the patients are registered and who their surgeons are and who their medical team is. Okay. A second part of it is that perhaps if you were the surgeon that extracted an organ, a kidney, I may think that you do a good job or not, and on the basis of that, I might accept or not accept a kidney that you have extracted as opposed to somebody else, perhaps. And our simulation procedures account for that. We can see the acceptance rates by across various pairs. And so I didn't go into the details of the simulation process, but it says, okay, there's a probability with which some transplant center might reject an extracted kidney from another one. And so those types of frictions are built in. And that's one of the things that's great about using data to try to design and engineer these systems, because you can look and build in these real-world considerations, which would be theoretically interesting but quite challenging practically to do. So that's one of the value adds of the data, to really mimic what's happening in the real world.
Can we hand a mic here? This table, please. I would also urge the students to ask questions after this. No, go ahead.
So this case where demand vastly exceeds supply, in your market design studies, do you look at people who are trying to game the system? Is that also part of what you're thinking about?
Yeah, so there are various different types of gaming issues. So in school choice mechanisms, I've explicitly studied gaming of the school choice system. Currently, I'm in the process of studying heart allocation. In heart allocation, if you undertake a certain kind of therapy, you get higher priority because it historically indicated that you were sicker and you would die without a transplant, but then we found that people would live long. So when we increased priority for these people, not surprisingly, more people took on this therapy. So that's a type of gaming, and you're going to think about how much of that gaming occurs versus what's a signal in that therapy, and try to balance those two things in order to think about what's the optimal level of priority. And so those are issues that come up here as well.
Yeah, don't you run into problems of values at some stage? Because, I mean, better, what is better is different for different people. So that's a very serious issue. How do you deal with that?
Absolutely. So I went over that graph quickly, but there were a couple of axes on that. Both axes, in some sense, were preferable, but how do you trade those off? That's one example. When I discussed the life years maximizing problem, you have this trade-off between trying to increase the number of life years or transplanting the sickest or not. So I think of this work as having two parts. One is positive economics to sort of predict what would happen in an alternative design, and then to exposit under a range of ways of evaluating those designs, what wins out and what are the trade-offs there. And then I think as an economist, I should stay relatively silent on what the ultimate thing that the policymaker would like to use, and the medical ethics community would like to implement. But at least I can give you guidance on what is likely to happen if you make a particular policy change. Yeah.
Thanks, Nikhil. So, quick question: Is there some sense of incentive compatibility in your mechanism design? For example, either at the hospital level or at a user level, that they are at least as well off participating in the larger market rather than doing it locally?
Right. So, when I described the deceased donor kidney allocation system, you can place constraints like Pareto optimality. That might be what you might be thinking about, that no patient is worse off under the new design as opposed to the old design, and that's a constraint on the set of designs that are feasible. And you can find the solution to the constraint problem as well as the unconstrained problem, and you can see how much you're potentially losing by imposing that constraint. So what's that cost of that constraint? And then you can think about whether you would like to have that status quo bias or not. In the school choice systems that I've studied, that thing really comes up. There are deferred acceptance mechanisms and so on that are strategy-proof or incentive-compatible and to report truthfully, and then in that case, you can think about what the pros and cons are of imposing that constraint.
We'll take one last question.
Professor Agarwal, are there prima facie general things one begins with, such as, for instance, one should think first of people who are youngest because they have the longest to live? Is that a sort of general kind of normative prior? And then, of course, it can be overturned by specific cases. But so do you have very general criteria of that kind? Prima facie is important. Prima facie, if you're younger and you have the longest to live, then the aggregate utility is likely.
Yeah, I think I would avoid answering that question specifically in the same way that I discussed the earlier one. You can think about that prima facie evidence of favoring the young. Maybe you can use a Rawlsian criteria behind the veil of ignorance and think that that is an appropriate notion of justice. But there's also the Samaritan's dilemma. If somebody is sick and is likely to die without a transplant very shortly, should I not give that person a transplant? So I think that weighing those things are heavy questions, and I think that I try my best to tell you what is going to happen on those dimensions, and then leave it to either the medical ethics community, or there's some political processes that are also involved in these designs to think through that.
Thank you so much, Professor Agarwal.
Thank you.
And I'm sure you and our next speaker have a lot to discuss over tea. Our next speaker is Sushant Sachdev, Associate Professor of Mathematical and Computational Sciences at the University of Toronto. He was chosen as the winner of the Infosys Prize in Engineering and Computer Science by Professor Jayati Murthy, who is here with us today, and her panel. He is a pioneering in theoretical computer science whose fundamental contributions have profoundly impacted many algorithmic challenges underlying modern society. I invite him to come here and tell us more.
Thank you. Thank you for that generous introduction, Bhavna. Thank you all for coming here. It's with my deepest gratitude to the Infosys Science Foundation for this honor and this privilege to present a glimpse of my research at this forum today. May I have a clicker? Excellent. I'd like to tell you a little bit, show you just a little taste of the kind of work I do. Maybe the title doesn't make any sense, but hopefully it'll at the end of the talk. Our real world is pervaded with large networks, right? Like that's the highway map of India. Huge, lots of intersecting roads. The internet in the bottom right corner, the social graph, Facebook network, or even biological protein networks. These are huge networks of interacting pairs of objects. We model these networks as graphs. So as an example, if you think of Facebook, right? Like every person in the world is a vertex, and I'm going to connect two of these vertices if the two people know each other, right? That gives me a really huge graph of 7-8 billion people. Today, so the networks that we are interested in have billions of edges and nodes, if not hundreds of billions. And if you would like to solve a computational challenge on this network, as an example, on the internet, let me send a message halfway across the globe. How can I do it really quickly and efficiently? You need algorithms, right? You need efficient algorithms for solving these computational challenges. That's what I work on. And let me sort of give you a brief manifesto of the kind of algorithms we seek to design. So I would like to design algorithms that have excellent running time guarantees, right? Like you give me a problem size, I will tell you that the algorithm will not run for too long. It can solve the problem really quickly, ideally in amount of time that sort of scales linearly with the size of the graph. If the graph grows 10x, my runtime only grows 10x, rather than growing up 1,000 times. I will want to prove its correctness. I would like to guarantee that the answer generated is correct, let's say at least with high probability. And finally, maybe most importantly, we'd like them to perform well in practice. So broadly, my research vision is to develop a complete toolbox of algorithmic primitives that we can utilize for solving optimization and learning challenges on graphs. And today, let me present to you a vignette from my research of one of the most popular or well-studied graph optimization problems in computer science. That's a problem called maximum flow. This is a problem that has been studied for over 70 years, right? It was formulated during the time of Second World War. In fact, this image on the right is capturing maximum flow. It's in a textbook, it's in a paper from 1955 by Harris and Ross. And it's showing the Soviet railway network. And if you notice, I think it's maybe too small to observe, but at least on the top right corner, you can read origins. And on this left, there's a circle called EG, that sort of is egress, right? It's really trying to model a network where something comes in from the origins, which is their factories, right? Like supplies for the Soviet network come in through the factories. Egress is the front line of World War II, where the soldiers are really fighting and supplies are needed. And you want to send your supplies as quickly as possible through the railway network up to the front line. Max flow really captures this problem in abstract. I will define this a little more formally in a second. Right? So this problem has been studied for basically 70 years, not just because it's an elegant formulation and captures something practical, but also because it's a very powerful algorithmic primitive. There are many optimization problems we can formulate on graphs that don't exactly look like maximum flow, but basically can be solved via maximum flow. And in computer science over the decades, this has served as a very effective test bed for development of new algorithmic techniques. So it's a favorite amongst algorithm designers and theoretical computer scientists. So let's roughly formalize this problem to tell you more. We will capture this network as a graph, right? So we have two special vertices, a source S and a sink T. Every connection, a railroad network, gets transported to an edge in this graph, right? And every junction is a vertex. And these numbers on these edges capture the capacity of the edge, right? How many railway lines in parallel, or how many goods can I send across this road, specific road? And then my goal is to answer that I want to route the maximum amount of goods simultaneously from the source S to the sink T. How much can I route? Does that question make sense? Right? There's a start, there's an end, and I have many, many paths I could take. Like, you're in Bangalore, right? Like, let's go from Whitefields to the other end of the city. And I want to send the biggest motorcade possible. I want to take all the paths and flood them. How many people can travel simultaneously so that we reach the other side of the city? Right? This problem is captured via maximum flow. So, how do we think about this problem? Let me give you a modern perspective. Right? A modern perspective really thinks of this problem in a more general linear programming way. That's a very powerful language from optimization. I'll give you a 2-slide version of how to think of this. So my flow, F, I won't use more math than that, is really just a set of numbers on the edges. So for every edge, I have a number. That's in purple there, right? Of course, not every set of numbers is a flow. So I have some constraints on this flow. I want this flow to be non-negative. This number has to be non-negative. And it has to be smaller than the capacity of the edge, right? If only 2 cars can go simultaneously on a road, well, I can't send 10. So that's the capacity constraint. And there's a directionality constraint, right? It's a one-way road. You can only travel in one direction. Very good. There's a second kind of constraint, which is that at every vertex that's not a source of the sink, the flow coming in should be equal to the flow going out. The number of cars coming into a junction should be equal to the number of cars going out. There are no cars staying at the junctions, right? So flow coming into each vertex is the same as flow going out. These are actually very simple equalities and inequalities. And together, this can be thought of as linear program. So linear programming is a very powerful language from optimization, and we can think of maximum flow as a specific instance of the linear program. And all you want is that subject to these constraints, I would like to send the maximum amount of flow through this network. So far, this is only the formulation of the problem and how we want to think about it. Now, let me take the rest of the time to try to give you one small insight that helped us solve this problem efficiently. So in this paper in 22, we gave the first ever almost linear time algorithm to solve maximum flow in almost linear time. This is almost the first progress on this problem since 25 years. And since I said it's a very powerful primitive, we don't just get fast algorithms for maximum flow, we get fast algorithms for all of these problems that people have written hundreds of papers about and did not know fast algorithms for previously, right? Or did not know almost linear time algorithms for previously, and this is the first time we are able to achieve almost linear time algorithms. So, okay, now let me try to present to you one key insight. So I said maximum flow is a linear program. How do we think of this? It's very easy to actually think of geometrically, right? We said we have some constraints. Okay, each flow number is non-negative because it's a one-way street, and it's bounded by the capacity. You should think of them as walls in a high-dimensional space that constrain you on one side of the space, right? So I'm drawing here a collection of walls. Think of this, this is 2-dimensional, but I'm sure you can all imagine 10-dimensional spaces or 100-dimensional. In this space, you are now bounded by these walls. Within this polytope, I want to find the point that's farthest along a fixed direction. This is linear programming, okay? Now you know what a linear program is. And Since max flow is a linear program, we're going to try to solve it as a linear program. How do we do this? The classic way is we'll define a potential. Right? A potential that's going to keep you away from each of these walls and yet decreases in the direction of the cost. Right? So if you see these contours, the potential is rising along the walls, but it's decreasing in the direction that I want to minimize. So all I need to do is I can step slowly along this decreasing potential, and I'll eventually reach an optimum that will allow me to solve the linear program. All right, let's apply this to maximum flow. Okay, to do this, to apply such an algorithm to maximum flow, you need to specify how will I take this step. Here is a classic way to take this step. I'm at a current, I have some flow through the network. I want to improve it slightly. How do I improve it? Mathematically, the way to do it is that I'm going to define a neighborhood around my current flow via this ellipsoid. This ellipsoid lies within my polytope, so I'm good, I'm still satisfying my constraints. And within this, I'm going to try to find the point with the minimum cost, right? Improve my flow as much as possible as long as I'm within the ellipsoid. If you do this for maximum flow, this is excellent because it turns out this is a very elegant problem. It's equivalent to sending electrical flow in the graph, right? You connect the graph as resistors, and I send 1 unit of current at the source and draw it at the sink. And electrical flows is a problem we know how to solve efficiently. So does this give us a fast maximum flow algorithm? Well, kind of. What is the problem? The problem is when you send electrical flows, if I connect a battery across a network, every wire in the network will have some current, right? So you have some flow on every single edge. That's not good because now that means I have to change the values across the entire graph. And if I have to do that many times, my algorithm will not be fast. So our key insight was that we will actually end up taking smaller steps, okay? Not in the ellipsoid, but let's take a simplex inside the ellipsoid. The guarantee now is that the point minimizing this, which is an end of the simplex, is actually very simple. It will only have flow along a simple cycle in the graph. Far fewer edges than the electrical flow, right? It's a much simpler update to my flow. And with this much simpler update, we can put it together and actually build a large data structure that can process these updates really quickly and give you a fast algorithm. So that was one key insight that gets us to the fast algorithm. But we can, the power of the framework is that we can really push it much further. We can solve flows with any convex loss. We can solve flows where edges are being added to the graph, or we can solve flows where edges are being deleted from the graph as the graph is changing. All of this in almost linear time. But where do we go from here? Well, we're almost there, but we would like to design almost linear time algorithms for all graph problems. There's still a few remaining, but even though we nail most of them here. And more importantly, we'd like to distill these insights and see if we can push them further and push them into algorithms in practice and really make a difference. With that, I'm going to steal a slide from Katesh's idea and really firstly thank all the funding agencies and institutes that have graciously supported me over the years and all this work, and thank my biggest supporters, my family, without whom this work would be impossible. Thank you all.
Thank you so much. We really hope that you apply max flow to our roads, but of course, we'll take some questions.
I think Bangalore really needs it, right?
Yeah, we need it. Any questions from students or from any of the academia? Yeah.
Hello. So how can this be implemented in a set of data for say protein networks? So when we analyze RNA sequencing data and all, we get a huge number of connecting networks which is quite hard to track, like what is connecting. There are sites like String that do help us in finding the connections, but what is connected where or how much is the connection, it's quite hard to analyze. So how can this algorithm help us in that aspect?
So, right, so maybe I'm missing what is the algorithm problem you would like to solve on the RNA network or the protein network?
So for example, there's one protein that seems to be connected to a lot of other proteins, like maybe via its interactions or maybe during its mRNA analysis and all. But to find out like what interaction happens in the first, which leads to further, is that something that this can solve, this algorithm?
It might be formulable, but I'm not sure I see the exact
Correlation.
currently.
Yeah. All right. I
Right,
just wanted to ask because it seems quite relatable.
It's very plausible,
but
it probably need to sit on it
sure,
offline
sure,
to connect.
sure. Thank you.
I think there was a question here. I think there's a question. Yeah.
Hi. Very interesting ideas. I wanted to ask whether there are general principles that might characterize efficient networks. For instance, in the brain, there are 80 billion with a B neurons, and each neuron connects with a subset of other neurons. And an emerging idea is that of small world propensity, which is that there has to be a balance or an optimal relationship between the number of edges and the path length, which is an important variable for information transmission, at least in nervous systems. So what principles might we derive from work such as yours?
I think that's a very fascinating question. There's been actually a lot of work in computer science trying to think about properties of what does it mean. Here is a efficient network in many different axes. My work relates, but it's more on the sidelines, but I can actually give you a more direct answer as to the directions where people have thought of this. So small world is one way in which people characterize, right? Like for those who haven't heard of it, small world networks are really where any two vertices in the graph will be connected via a short graph. And the main observation comes from that any two people in the world can know each other via 6 acquaintance hops. But computer scientists really like this notion of what are called expander networks, or you should think of them as roughly random graphs. So these are really low degree graphs. You can think of every person is connected to 3 or 4 neighbors, and yet these graphs behave almost like completely random graphs in the sense that you cannot partition the graph into 2 parts without cutting a lot of edges. It turns out these random graphs behave like these expander graphs, which are actually deterministic, behave like as if they're completely expanding and give you many, many more properties of being well connected, very good maximum flow. They also have eigenvalue connections. Right, so there are many multiple axes along which they have defined what does it mean to be an efficient network. And it's related to maximum flow, but not completely.
Yeah, Professor Kulkarni.
Yeah, so let's go back to your first paper in 1955 that you talked about.
Okay, not my paper,
okay,
but yes.
And to a problem imagine yourself in 1940 now.
Right.
In that case, if I was in Russia, I would be very interested in the minimum flow problem. No, if I was the enemy, I would be interested in the minimum flow, which is which junction do I destroy?
You are exactly right. I didn't want to phrase it in such a negative context, but this is exactly the formulation that the other side of the world formulated. Which are the junctions that you should break in order to break the capacity of this network?
But that's also even relevant today. Not so much that we're at war, but if we have an internet network, I want to know where are all the weak spots, because that would require more reinforcement.
That's perfectly right. Like, for example, really in today's traffic network, right? Like you have some sense of where traffic begins and ends, and you can analyze it in terms of bottlenecks. And there's a very formal sense in which the dual of the maximum flow problem allows you to capture bottlenecks in the graph and identify which are the sore points. And if you were to increase the capacity of all the bottlenecks, the amount of congestion in the network would go down.
Well, a fascinating talk. Almost linear is great,
Yes.
but it's also, it's almost linear in edges, which is probably quadratic in number of nodes. So even that is large. Are there any attempts to now go sublinear with sampling? And it might be connected to something else. When I was looking at the picture, when you were drawing the ellipsoid, it reminded me of a stochastic gradient descent quite a bit.
Mm-hmm.
So you guys, any connections to that as well?
Very, very, very good questions. I think so. There are definitely works looking along it. It is possible to replace a dense graph with a sparser graph without not much loss in the pairwise capacity of sending amount of flow. Let's say you just want to lose at most 10% of flow between every pair. It is possible to replace it with a sparser graph, but we don't know how to do it without actually looking at the entire graph. All right, and in some sense, it's like there is also attempt at trying to do these things locally. Like for example, if I only want to transport goods within Bangalore, I don't need to look at roads outside of Karnataka, right? Like we sort of have this intuitive sense that it would make no sense to take such a long detour, but that's a very local sense of operation, and the kind of algorithms we would like to say give guarantees. Oh, give me any pair and I will give you an answer. But there is work on trying to do local algorithms which will be able to send flows without looking at everything. But in the worst case, you do like if I allow an adversary to pick the endpoints, I do have to look at the entire graph to even know whether I can send a single unit of flow across the graph.
We have time for 2 quick questions. We have loads of questions. I think there are 2 already.
Yeah. You talked about identifying bottlenecks and then enhancing, I suppose, flow through those. But in fact, in traffic networks, very often, if there's a bottleneck and you build a dedicated flyover or bypasses there, all that happens is many more people make the choice of using those and you actually solve nothing. So are there any insights in your work on this kind of question?
I think the insight is in your, rather than, our work does not shed any direct light on really, in some sense, a market design question that you've asked. Right. When people are acting selfishly and they are allowed, the demand can go up and down, it's not entirely obvious what happens when you increase capacity, and you can sometimes get the opposite of the intended effect. And it's in fact a very famous paradox called the Braze paradox, where adding a flyover with zero cost can actually lead to increased congestion across the network if people are acting selfishly, even without the demand increasing. My work does not act on these dynamic settings, but it's definitely a very interesting direction that actually computer scientists have studied at length.
I know there are lots of questions. We'll take the last one right now, and then we'll do more over tea. You're very popular today, Sushant. So do give us more of your time at tea. One more question.
Happy to.
Thank you. Fascinating talk. So I'm just asking this because you talked about large networks. But this presupposes knowledge of the capacities and the entire network structure.
Yes.
You may have local knowledge.
Yes.
You talked about local flow problems in the localized way.
Right.
So how would you actually take this to large networks if you don't really have the entire flow capacity? Or some version, maybe some network statistic in terms of flow capacity or something of that sort.
I think very good question. Our algorithms sort of presuppose, in fact, they presuppose exact knowledge of the exact edges and their capacity, not even some like, oh, I have some uncertainty on some edges. They are really in a I know everything, I just want to compute the answer setting. No, that's a very good question. I'm not sure I have a good answer to this. I think like maybe do you have a concrete example in mind as to what kind of networks? Like you probably have to experiment to actually even obtain the capacities of the edges.
We'll give you food for thought with your chai.
Yes.
Thank you so much.
Thank you. Thank you all.
Andrew Allocate is the Associate Professor in the Department of South Asian Languages and Civilizations at the University of Chicago. He's considered the world's foremost scholar of the Prakrit languages in this generation, and a panel chaired by Professor Akhil Bilgrami has chosen him as the winner of the Infosys Prize in the Humanities and Social Sciences. I request him to tell us a little bit more about why in today's hyper-modern world of absurdly fast algorithms, linguistics and ancient languages are still important.
Good afternoon, everyone. Thank you, Bhavna, and thanks, of course, to the Infosys Science Foundation. My name is Andrew Allocate. I'm a philologist, which means that I try to understand the past through its texts. And as with any field, probably, there are a lot of convenient fictions that we use to organize our knowledge of the textual past. In the case of South Asia, the textual past is truly immense. We have dozens of languages, hundreds of thousands of texts, millions of manuscripts spanning roughly 3,000 years. So we can be forgiven for relying on some of these fictions. But once you start working with some of these texts, you begin to see just how fictional they are. So this image is from Kobatirt, a large manuscript library just north of Ahmedabad. So let me give you an example which will introduce some of the languages I work with. In terms of their linguistic development, we can classify one group of related languages into Old Indic, Middle Indic, and New Indic, as this scholar, well, writing in German in 1886 did. This is a modern, or in my world, a modern scientific classification based on the principles of comparative philology. But you'll notice that he attaches a traditional Indian word to each category as well: Sanskrit, Prakrit, and Bhasha. Now, it would be very convenient if these languages occurred in a linear sequence, as shown here. This is how we imagine they must have developed, in some sense. But when we actually look at their history of attestation, it's not so simple. Whatever else it is, language is a cultural practice, and hence, if we want to understand its use, we need to understand the complex cultural forms in which it is embedded. Hence, rather than a unidirectional development from old to middle to new, we have to think about the simultaneity of languages and their influence on each other. I will come back to this slide. So one image of simultaneity is the description of Indian languages that Mirza Khan includes in his Tuhfat al-Hind, with which I began my book, Language of the Snakes. So he writes, "It should be understood that the people of India have a number of languages, but those in which books and poetical works may be composed, such as would be agreeable to those who possess a refined disposition and straight understanding, are of three kinds: Sanskrit, Prakrit, and Bhasha." For Mirza Khan, these were not languages that followed each other in a historical sequence, at least not primarily. They were languages that existed side by side. They were related to each other not in terms of linguistic development, again, not primarily, but rather by the different uses to which they were put, and specifically literary uses. And although he wrote this in 1676, the overall picture would have been the same, roughly the same, 1,000 years before that, maybe even 1,500 years before that. So consider, as another example, a Kannada verse that was composed around the year 870. Sakkadamum pagadamum avakkum bagadante samariperam munnam nikuvam olavapudarin takkant avaravar lakshyamum lakshanamum aridadam kannadarol tirikuregundariye pelven embudidargam. So Sanskrit and Prakrit used to be what came to mind to write refined literature. Because they've always been around, they each have appropriate models and norms. Lakshyamum, lakshanamum. But it's completely impossible for anyone to go around collecting scraps in the field of Kannada and then to claim to make it intelligible. So this is a verse explaining the difficulty of offering advice or prescriptions about composing Kannada at the initial, at the very beginnings of Kannada literary history in comparison to Sanskrit and Prakrit. So the incredibly persistent structure that Mirza Khan was describing was what I call a language order. So for me, the term language order refers to the way that languages are ordered within a culture, the recurrent patterns and schemas and tropes by which they are defined and represented, the names under which they're known, and the values with which they're associated. So this is basically what I wrote my first book about. So let's get back to Prakrit. You see this occupies a central place, quite literally, in the very simplified version of the language order that Mirza Khan has sketched and that I give here. So my wager was that if I could understand Prakrit, this strange language that Mirza Khan called the language of the snakes, then I might gain some insight into the language order of which it forms a part, and hence into the whole complex of literary languages in South Asia. Prakrit is known to anyone who's familiar with Sanskrit literature because what we call Sanskrit plays are actually Sanskrit and Prakrit plays. Prakrit is assigned to certain characters, mostly women. And here we have the most famous Sanskrit play, Kalidasa's Recognition of Shakuntala, Abhigyana Shakuntala. I would guess that about 30 or 40% of it is composed in Prakrit. Here, the purple lines indicate the speakers who speak in Prakrit. This is just a random page from the play. And the orange lines indicate the king, Dushyanta, who speaks in Sanskrit. And since I mentioned Kalidasa, I wanted, and because my colleague Naresh Kirti is here, I want to mention that with Naresh, I'm working on editing and translating a play that is arguably just as good as Kalidasa's Shakuntala, but hardly known to anyone. It's a play about King Udayana, called Udayana the Ascetic, Tapasa Vatsaraja. It is also composed in a mixture of Sanskrit and Prakrit. It only survives in one manuscript, and the Prakrit, which you can identify here because the scribe has written some of the Sanskrit glosses above the Prakrit words, it needs a lot of help. But even apart from plays, there's a whole universe of literature composed in Prakrit. Lyric poetry, story literature, court epics, commentaries, even technical and scientific works. Here I just show you a very fragmentary inscription in Prakrit that seems to refer to a military victory of the Paramara king Bhoja, a very famous king in the 11th century. And so this is actually from Bhoja's palace in Dhar in Madhya Pradesh. So if we look at the big picture, the truly big picture, including the various ways that Prakrit has been used and talked about over the many centuries of its existence, it seems to take on these contradictory attributes. Is it one or many? I usually say Prakrit, other people say Prakrits in the plural. This is the question that I get most often. Is it one language or is it many? But this is a question that we can and should ask about all languages. What does it mean for a language to be one language? We can ask this about English or Kannada or Hindi. Is Prakrit regional or transregional? Many people will know that varieties of Prakrit are sometimes named for regions of India. This is very, very misleading for reasons that we can talk about later. Is it elite or popular? The name suggests that it's popular. Prakrita means kind of natural or common, but we actually only have mostly elite literature. Is it cosmopolitan or vernacular? To use a pair of terms that was introduced by my teacher, Sheldon Pollock. The Natya Shastra, an ancient Sanskrit text on theater, captures some of these contradictions when it says that Prakrit is the same as Sanskrit, but opposite, whatever that means. This makes Prakrit pretty difficult to fit into a single conceptual scheme, especially one based on binary oppositions. For example, it almost kind of looks as if Prakrit represents the everyday speech of regular people. If you read Prakrit, you can kind of get carried away into that belief. But then you're inevitably reminded that it is just as much a learned, cultivated, and literary language as Sanskrit. So it hangs between these opposites, like Trishanku here, suspended between heaven and earth. But the same contradictory character also makes Prakrit unique and interesting, not just to me, but to many generations of Indian readers and critics. Prakrit lyric poetry, for example, was treasured for its apparent simplicity, but when you thought about it, that simplicity revealed complex depths of meaning. So these are some of the points that I've tried to make in my engagement with Prakrit literature in Language of the Snakes and beyond. So one of the projects that I'm working on right now is an edition, translation, and study of the Kaviraj Margam, The Way of the Poet King, the earliest work of Kannada literature to survive. This was composed during the reign of Amogavarsha, so maybe around 870, maybe a little bit before that. I'm working on this text with Sarah Pierce Taylor. I surreptitiously quoted from it earlier, and it's essentially a guide to writing literature in Kannada. And as the very first work in this literary tradition, it has a lot of preliminary material to cover. How do you actually go about this? How do you compose in a language that very few people have composed literature in before? We can think of it as a sustained reflection on vernacularity, looking at the same language order that I had been studying from the vantage point of Prakrit, but this time from the vantage point of the Pasha. I think I will wrap it up there, and thank you for your attention.
Thank you so much. I just love the interdisciplinary nature of questions that we've had so far. Does anyone else? We have a question here, 2 questions. Oh, sorry. No, go ahead. Please go ahead, and then we'll take questions.
Such a beautiful work. Thank you so much. I just had 2 questions for you. One is in the Valmiki Ramayanam, Hanuman mentions Manushya Bhasha. I didn't know where that comes in. And what is the place of Tamil when you are looking at Prakrit and all of that evolutions?
Yeah, Tamil is also a very difficult language to place in these schemes that are very binary. Is it classical or popular? And is it vernacular, or is it regional or transregional? I would say that I'm not being a specialist of Tamil literature. I'm going to decline to answer that. It's very complicated, and we're learning a lot more by the day about the history of the Tamil language. So, which is great, of course. But yes, I mean the Valmiki Ramayana, in that very same passage where Hanuman says, "Okay, I will use Manushya Pasha," that he entertains the possibility of using Sanskrit, and that I think is the first time that Sanskrit is used to refer to a language.
Wonderful. Thank you.
Thank you, Andrew, for a very, very nice presentation. I have one observation. I wonder what your reflections on that might be, which is this kind of idea that, in a certain sense, by studying these texts, which is the choice, obviously, that you have. One is constrained by that, right? But one is the fact that you have had what you showed, for example, the fact that, that there are manuscripts which for 300 years nobody has even turned the pages on. And yet, obviously, a lot of theoretical formulations are made, such as it's only the East India Company which brought modernity in India, and so on and so forth. So that's one part, really, that there is a huge amount of textual material which there seems to be no interest. So thank you very much for taking such an important initiative in these matters. But I wonder if you have any observations on, what are the modern assumptions which make that into something which nobody needs to look at in some ways, because it comes in the way of their theorizing, probably. I don't know. The second was this question that, if one thinks about the fact that the women's speech, and you give these lovely ones from Abhigyan Shakuntalam, what is very interesting to me is that these are men writing, right? And they yet know women's speech so well. So they know so well that Anusuya does not talk in the same way as Priyambada does, for example. Yeah. Fantastic understanding of variations of women's speech. But we obviously have no access to how women knew men's speech, right? Yeah. You get this a little bit when you get citations, for example, when women are citing men. But I wonder whether that puts a constraint in some way of how one interprets, very neat language order, because there's a huge amount that is missing over here, which is really women's speech, right?
Yes. So I can respond to this question. Thank you for these questions. Maybe one answer will do for both questions, which is the question of absence. What I have been trying to do is make sense of the literature that we have, which is a very, very small fraction of the literature that was produced, because it's the literature that survives. And that is not representative of human discourse or human life at all. That is representative of very specific kinds of cultural activity. And as I totally agree with this. We simply we haven't read the texts. Nobody has read all the texts. This is a massive archive that is impossible for even a kind of generational project to understand. So yes, I think that when anyone generalizes about the textual past, you need to really hold on to your wallet. But I have tried to invite more people to participate in this research precisely for that reason.
In your Kaviraja Margam quote, it's interesting that the author compares Kannada to Sanskrit and Prakrit and not to South Indian linguistic precursors.
Yes.
Is there something to be understood there?
Yes, there is, which is that you would think that other languages besides Sanskrit and Prakrit would be mentioned. So for instance, Tamil, which has by this point, a long grammatical tradition and a lot of grammatical writing. Tamil is never mentioned in the Kaviraja Margam. It's never mentioned in at least the first couple of centuries of Kannada literature. Very, very interesting. Telugu is a different case, but yes, for some reason, it's just not on the map.
Thanks.
Thank you for this fascinating window into a whole new world. I want to touch upon something related, but maybe not the same. Do we know, text is at least one medium that has survived, but are there any sources of hints as to how these languages evolved as they were spoken? Let me just take a specific example. There seem to be enunciations of consonants that have diversified within the Indic languages, modern day Indic languages. Yeah. And I wondered if there is a way for us to answer how this evolution happened, or how were these languages spoken 5 centuries ago or 10 centuries ago. Do we have any hints of how they were vocalized and how were they used, how were they spoken in a day-to-day basis?
Yeah, I mean, we basically have 2 sources. One is comparative philology. You start from the way that languages are spoken now and you try to work your way back. You come up with something that looks, in many cases, looks very much like Sanskrit or whatever, depending on the languages, but is going to be different in interesting ways. The other possibility is that we have, so these texts that I study are mostly literary language, written in literary languages that are kind of fixed in time, but once in a while, they will give you kind of snippets of everyday vernacular speech. And so there, our first evidence for Hindi, or as it's called in this text, Madhyadesi Bhasha, is from a Prakrit novel of 779 CE. Yes, I mean, it would be nice if there were like phonograph recordings, but there aren't.
From this table. Andrew, that was really fascinating, right here. I'm curious about the evolution of punctuation in writing. So a lot of the texts you show, they are free-flowing. And I wonder when punctuations, or whether there are certain cases where you see some punctuations or structuring being used, while in other cases it's a free-flowing writing, and whether that says something about what these were written for.
Yes. So I've learned, I used to hear things like, well, certain types of punctuation are very modern, or certain types of punctuation didn't exist. And then I've, following Professor Das's question, I've learned to just avoid all generalizations like that, because our earliest example of interword spacing is in the Ashokan inscriptions, the earliest example of writing in South Asia. So there was some form of punctuation, interword punctuation. But then after that, people seem to have abandoned it. And it was only kind of reintroduced later and probably independently. But yeah, there's many different kind of regional and kind of stylistic punctuation systems.
So you mostly talked about novels and plays in Prakrit. So in Sanskrit, we also know that mathematical formulas or scientific facts were recorded in Sanskrit. Is there any evidence or indication that similar things were recorded in Prakrit as well?
There's yes. I mean, so there's a couple of texts that mostly are concerned with astronomy, that from within the Jain tradition. But they also include some, I mean, I've looked at these texts and then not understood them, so I didn't read them very seriously. But yeah, they introduce lots of calculation techniques as well. So these are like first millennium Prakrit texts from the Jain tradition. Yeah.
Sorry to cut this short, but we're running out of time. We'll accost Andrew over coffee and take more questions there. Thank you so much. Our winners are true polymaths this year. We all know how important DNA is in the scheme of life. Did you know that the cells that house these DNA are under attack daily, around 10,000 times? What happens when DNA strands are broken? How are they repaired? Anjana Badrinarayanan, Associate Professor at the NCBS, has been chosen as the Infosys Prize winner in the Life Sciences by Professor Mrigank Sur and his panel. I would invite her to come and tell us more about her work.
Thanks, Bhavna. You can hear me okay, right? Yeah, okay. Thank you very much, Bhavna, and huge thanks to the Infosys Science Foundation for this honor and also for the opportunity for me to share with you some of the work we do. I'll give you a sort of a brief outline of what I'm going to tell you about. I'm going to try to tell you about what we are motivated to do in our lab. I'm going to tell you about some of our discoveries and then give you sort of an overview of where we are going next with the tools and the insights we've gained so far. And I'd already like to say at the outset, all of the science we do is really a group effort. And so I'm extremely privileged to talk to you about the work of all these fantastic people I've had the privilege to work with. All right, so, Francois Jacob has been attributed to saying that the dream of every cell is to become two cells. Now, that's the fundamental definition of life, to duplicate and reproduce, right? And within this, there is really one thing that a cell needs to do well, and that is the ability to package its genome and take it across subsequent cell divisions to make sure that the cells get genetic material accurately. Now, DNA is the fundamental unit of life. It encodes all information required for the cell to function, and it's really quite a fascinating molecule. This is an early electron micrograph of an E. coli, a bacterial cell, lysed, with all of its DNA spewed out in these sort of loops coming out. Now, this DNA is compacted nearly 1,000-fold to fit inside a living cell. And inside this really tiny space, this molecule is replicated, segregated, and given to daughter cells accurately. And all of this information is maintained so that you get life to function not just at a unicellular level, but all the way at our scales of living. Now, it's not just a problem of packaging. You don't just need to make sure DNA is compacted and fit into these tiny volumes and faithfully replicated. This really important molecule is actually quite unstable. I like to say that life itself is damaged. So ever since life kicks in through internal and external sources, including metabolism, irradiation, DNA stress, for example, the DNA gets constantly broken. In fact, estimates suggest that every day, a single cell inside a human body goes through 10,000 DNA damages per cell per day. And this gets fixed really accurately. But over time, of course, you get some mutations that result in diseases, but also are the underlying cause for aging. And so DNA damage and its repair are really important for cells to survive. If this goes wrong, you see these monster cells, for example. This is when cells have faced DNA damage, and they're not able to propagate the way they're supposed to do normally. Now, DNA damage repair enables cells to adapt or evolve over time, and I'll tell you more about how evolution is enabled in the next slide. And also, when it goes wrong, it can result in pathologies and diseases, and over time, it can result in cell death, and also has implications for our understanding of aging. Now, in my lab, we're really interested in understanding how cells repair DNA. And cells are able to repair DNA via error-free mechanisms. So this makes sure that nothing changes about the DNA basis. So your genetic material remains the same. But sometimes cells can do something fascinating. They turn on mechanisms to repair DNA that induce mutations. Now, this is really important because a balance between making mutations and keeping things error-free allows cells to evolve. It allows cells to adapt to stressful conditions. For example, in case of microbes, it allows them to colonize us because they can evade our immune responses or our immune systems. In nature, it's really dangerous for microbes. They're constantly fighting with each other, similar to us humans. And so this helps them sort of deal with intermicrobial competition. And sort of more relevant to our human health, this is an underlying cause for how antibiotic resistance develops. And so we look at this balance between error-free and error-prone DNA repair mechanisms in my lab. Now, how do we do this? We really like to watch molecules in their natural habitat. So we use microscopy primarily as a way to ask how cells manage to know there is damage and then manage to mount repair pathways that help them fix it. So we do microscopy that enables us to track molecules and pathways at high spatial and temporal resolution, and we quantitatively analyze them to derive mechanistic insights into how these pathways function inside single living cells. We combine our approaches of microscopy with systems or mechanisms to perturb the cells so that we can watch when a perturbation occurs, how cells deal with this. And then we have other methods also that we apply to really get molecular insights into what's going on inside a living cell. We've used two big model systems in the lab. We've used mitochondria from budding yeast, and we've also used bacteria, a really cute bacteria, I would like to say, called Colobacter crescentus. It's benign to us, but is a fantastic model system to understand DNA-associated processes in living cells. What I'm going to do now is I'm going to give you sort of two snippet stories of what we have, how we've used these tools that I've just told you about to discover something about how DNA repair occurs inside cells. Now, the first one, I was going to, first before that, I'll tell you we've looked at pathways of DNA replication, DNA recombination, and how cells mount stress responses to deal with DNA damage. Now, the first discovery I'm going to talk to you about is to do with mitochondrial DNA maintenance, how cells maintain their mitochondrial DNA. Now, as I've already told you, for life to propagate or sustain itself, cells need to protect their DNA. So this is an average eukaryotic cell, and this is the nucleus with this chromosome shown in these multicolored threads. They also need to copy and segregate their genomes, as I've already told you. But with eukaryotic cells, there's one other problem, which is the protection of DNA. And we know a lot about how this nuclear DNA is protected, but we know very little about this other piece of DNA that exists in eukaryotic cells, and these are mitochondrial DNA. Now, mitochondria are known as the powerhouses of the cell. They what generate the energy required for our cells to function. And interestingly, these organelles, they carry their own DNA that autonomously replicate and segregate. And these DNA can face a lot of damage in the mitochondria due to the metabolic activities of the mitochondria itself. And so what we don't really know is how cells respond to this type of DNA stress. And one of the reasons why we don't know about this is because tools to perturb the mitochondria have been missing. And so we did this. We tried to answer this question via building a tool to specifically target mitochondrial DNA, break it, and ask what do cells do then in response to mitochondrial DNA stress. And now it's really exciting for me to tell you that this tool has actually gone all the way from yeast into mice models, and it seems to show some really cool insights. But what did we find? Very, very quickly, we found that when you make mitochondrial DNA damage, it affects not just the DNA, but it affects the entire organelle. It changes the mitochondrial structure, so it goes from a really nice network to a fragmented state. It perturbs mitochondrial function. They don't function so well. And really shockingly, it results in DNA degradation. Now, this is counterintuitive because you would think that cells would protect the DNA. But what instead happens is that cells use the very machinery to copy the DNA to clear the damage out. I like to give this analogy like it's a Pac-Man. So you can think about this as mitochondria, and this Pac-Man going about chewing all of this DNA up in response to DNA damage. And it's possible that this happens because mitochondria have many DNA copies. And this may be one of the reasons why we have so many DNA copies in the mitochondria, because this is how they deal with DNA damage. They just clear out the damaged DNA and then make new copies from whatever remains. All right, so in another discovery I'm going to tell you about is a question that we've been fascinated for a really long time, which is how cells find matches inside the cell. Right? And the question of match here is going to be a question of homology. And this work really is an effort, collective effort of us doing the biology, but really physicists coming in and telling us what all of this biology means. So it's quite interdisciplinary in that sense. And so what's the question? The question is, how does a break site find its partner? And I'm going to try to break this down for you. So imagine you go into a large sort of fair, and you and your twin go at the very beginning, and this fair has 9 million people in it, and you get separated at the gate. And now you have to find your exact twin, right, in this 9 million people that are there in this fair. And you don't have a chance to call out to them. They don't have a chance to call out to you. So you really just have to search the environment to find that right match. Cells do this fascinatingly. When there is a break, when both strands of DNA get broken, that broken strand goes in search of its partner. And this is a cartoonic representation of what the search is. And it's a really complex process. Theoretically, if we were to count how long it would take for a single break to find its match, it can be anywhere between 30 hours to 3 days. In the cell, it happens in 30 minutes. Right? So there's something which we have not understood about how search occurs. And so we decided to tackle this problem. We built a system where we can track DNA repair and search accurately inside the cell. And we tracked the search complex. We tracked how search is occurring. And we found something really fascinating. We found that search is very dynamic. It occurs across the whole cell volume. So you can see the search complex, the break site moving across the cell, looking for its partner. And this is sort of a nice way, an easier way for you to see how this thing moves across the entire cell. We then went looking for what could be driving this motion, and we found molecular motors. So these are almost like engines, the way you would have in machines. And these motors can power the search. So if you remove the motor, you don't get this movement anymore. And if you don't get movement, you don't get repair anymore. And so now we found these molecular motors that do search inside the cell. We've solved somewhat the molecular mechanism by which these motors enable the search. And more importantly, it turns out that what we found in this humble bacterium Colobacter is the same mechanism that happens inside our own cells, right? So it's the same set of proteins doing this search process in cells. So it seems to be a universally conserved mechanism where multiple motors sort of power search, moving the break around, searching for its intact partner inside the cell. All right, so what we've been doing in the past few years in my lab has been to look at these types of processes in the context of a living cell. So, for example, we've looked at the process of DNA mutations. So we've done experiments where we've asked, when do cells mutate their DNA? And we found that mutations can occur in unexpected conditions. This means that, usually you think mutations occur when cells are active. They're growing and they're replicating. But we've done experiments showing that cells can mutate their DNA even in dormant states. So, for example, when you have an infection with a bacteria such as Mycobacterium, it gets dormant inside our bodies, and we think that these are inactive cells which would be incapable of developing resistance. But it turns out cells like these can have the ability to actually do mutagenesis and mutate themselves and can become resistant to antibiotics even though we think that they're actually dead or sleeping. We've done experiments to look at the DNA replication machinery, and we found these really interesting conundrums where the enzymes that are supposed to duplicate your genome also end up clearing the genome away or destroying them in some cases. I've not told you about this, but we've also looked at stress responses. How do cells respond to DNA stress? And we found that stress responses are heterogeneous, so each cell seems to do its own thing. But within each cell, the response is structured and highly predictable. And we've also found that searching for partners can be remarkably accurate and efficient inside the cell, explaining how search can occur within 30 minutes as opposed to this 30-day problem that we've thought of in the past. All of this now makes us wonder about what happens when there's foreign DNA. So all of these processes we've look at the chromosomes, so the stuff that's genetically inherited in a living system. But microbes are quite fascinating in that they can have DNA coming in from the outside also. This can be DNA from viruses, or DNAs that are present in these circular units called plasmids, which carry a lot of interesting genes on them, including genes for developing resistance to environmental conditions. And so we're really interested in understanding how cells deal with foreign DNA that's not normally present on their own genomes. And the same pathways are active in them also because the chemistry of DNA is the same, no matter whether it's a chromosome or DNA that's coming from outside. All right, and the reason why we're excited about this is because this has important implications to understand how microbes adapt to new environments, such as antibiotics, stressful environments, such as heavy metals and so on, and more interestingly, temperature. As temperature changes, how do these pathways now deal with their DNA also? Okay, I will thank all the people again who've done the work, fantastic collaborators, really grateful for all the funding support over the many years. And I will take questions.
Thank you so much. I'm sure we have a lot of questions starting right here. And then we'll start with Professor Kulkarni and somebody at the back after that. Yes. Just 1 minute. We'll start here first. Go ahead. Yeah, you go ahead.
Yeah, so one of the limitation of going to Mars is the DNA damage due to cosmic rays. So if we want to do that, which I think we should, and eventually to other stars, I don't know when, but Mars we should. Other than physical solutions like a lot of lead shielding, is there some, I don't know, some pills you can develop that speed up DNA damage in humans?
It's an interesting question. So, one of the bacteria we've been considering to work on for a while now is Dinococcus radiodurans, which is the world's most radio-resistant organism. It can tolerate up to 5,000 GY of radiation and has been quite interest to people who do space biology because it is an organism that should be able to survive in space. One of the key adaptations of this organism is its ability to do recombination very quickly, and that's the pathway where we do this. We look at the search kinetics, and so it's really, really good at doing that. And we've also done some comparative analyses of the sequences of the proteins that are involved in doing exactly the search, and those have changed specifically in Dinococcus radiodurans. So there are people who have done experiments where they've tried to do swaps, where they take these genes from more radio-resistant organisms and put them into human cells, for example, to see if they can become more radio-resistant. And sometimes it works. So maybe that's a good strategy. We've not considered it, but maybe we need to study these organisms more to see what else is going on in them. But recombination is certainly a key pathway that they have made better to survive radiation damage.
Ma'am.
Yeah?
Yes. Yeah. Especially in diabetic patients, their natural microbiota is disrupted in the intestine. So how this will be cope up with the solutions which you are trying to, and then how in lean individuals as well as in obese individuals, there is a difference in the changes in the microbiota too. So how this natural habitat can be restored with any of these mechanisms can?
Well, I can't directly answer that because we don't study microbiomes, so I don't know what's actually going on in them. Maybe they have some adaptations to living inside human gut, which is different between diabetic and non-diabetic conditions. I can't quite answer the question, unfortunately.
Because
Sorry.
in both the cases, the mitochondrial damage is happening.
Okay, so you're talking about mitochondrial damage, not microbiota. Okay, that's interesting. Yeah, I mean, I guess it's a fascinating question. We've been looking at how mitochondrial DNA repair occurs when there's damage in early mouse development. And there are some interesting things that we've noticed. For example, the mitochondrial DNA is released into the cytoplasm, and there are studies that suggest that this can trigger an immune response then via this pathway called CGAS sting. And so maybe something like that goes on in diabetic conditions. It's worth looking at, yeah.
Yes, and some of the other factors like oxidative stress are also causing them to directly cause a DNA damage.
Absolutely, yeah. I mean, so oxidative stress is one of the primary sources for DNA damage in the mitochondria. And we think that the main pathway for repair of such damage is DNA degradation. So local DNA degradation followed by resynthesis.
Okay.
Yeah.
Thank you so much.
Thanks for the very nice talk. I'm here, yeah. I was asking, you mentioned something about there being changes inside the cell even when it's supposed to be dormant. Yeah. So, of course, one's well heard of spores, which can last very long. So my question was, what other changes do you think are happening within spores? Is this true for them as well? And where do they get the energy from to make these changes if they're really in a dormant state? And yeah, that's the question.
It's actually a really great question, and I think the definition of dormancy itself is changing now. So earlier, dormancy was thought to be completely silent, but recently people are finding that although cells may be dormant in terms of things like DNA replication or protein turnover, there's still metabolic activity. And so there is low-level generation of ATP that can still power some of these mechanisms. There's also this new concept called transgenerational damage. So what these cells end up doing, and this is true for these radio-resistant cells especially, they cap up their DNA breaks with proteins, and those proteins then stay for a really long time. They can stay for even 100 generations on those breaks. And as soon as they get released into environments where they can grow again, even before they start replicating, the first thing they do is seal up the ends, and that way they survive. And spores are interesting because they have this complex called the non-homologous end-joining complex. And in bacteria, it's only sporulating bacteria that tend to have them. And people have found that in spores, the proteins are actually made and kept. And it's thought that this is to enable the capping of DNA breaks, if there are any, in the anticipation for an energy replete condition again, where you start growing and then fix the breaks. They're quite adept at this, waiting it out.
I see.
Yeah.
Thank you very much. That's very interesting. Thank you.
You mentioned an error-prone repair process that happens in dormant cells, but this must act in the face of a very active mismatch repair process that also occurs. Is that suppressed when cells are not growing? And secondly, is there a mismatch repair mechanism in mitochondria, where you mentioned that damaged DNA is simply degraded?
No, it's a really good question. With the mitochondrial DNA, there is no active mismatch repair. There is partial mismatch repair. The only exception is corals. So corals have long age, and they have an active mismatch repair mechanism dedicated for the mitochondria. But most other eukaryotes do not carry active mismatch repair. And again, the DNA degradation model just makes more sense in that case, because the mechanism we found is where the proofreading activity of the polymerase gets hyperactive because of how the DNA slides into this domain, and then it starts to chew the DNA up. And so it's almost programming error correction within the proofreading domain. With regards to the error-prone repair in dormant cells, this is coming via error-prone polymerases that act on gaps. And this would then not require or not compete with mismatch repairs, because it's not coming at mismatches, it's coming at gaps. And synthesis across gaps then generates the error. Yeah.
Yeah. Sure. My question relates to your first slide, to live is to replicate. I'm eager to know if there's any life form at all that's altogether devoid of nucleic acid. In other words, I mean to ask, is there any molecule apart from nucleic acid that is capable of self-replicating?
Well, some viruses use RNA, but they don't use RNA directly to self-replicate. They still get converted to DNA for replication. So I think in current day species, the answer is we have not found any, but in biology there's always exceptions, so I don't want to say no. But RNA is thought to be another solution for doing self-replication. Yeah, but and some viruses are RNA viruses. So I mean, there's that for certain. But it's still dependent on the host providing the ability to replicate the genome.
We'll take one last question.
Yeah, hi. It's a very interesting talk. Wanted to check with you if you've ever worked with CoQ10 enzyme in the process of this repair, or similar antioxidants.
Yeah, it's a nice question. So we actually did consider this. We've put so the question you're asking is, could you rescue the mitochondrial DNA damage just using either CoQ or superoxide dismutase or any other such antioxidant? We've not done it, but we've been considering it in the mouse model, whether we can reduce the ROS levels and see whether there would be less perturbation to the mitochondrial DNA that's getting then released into the cytoplasm. We've not done direct experiments there.
All right, okay, thanks. Because this could be a direct extension of what Professor Kulkarni was saying. Could there be a pill?
Thank you so much. I know we have a lot of questions and interest in your work. I'll say what we've said to the others. Over to you, please. Thank you. Thank you, Angela. Very often, pure math and mathematicians are seen as too abstract, a bit like art. Is it being done for its own sake, but it's beautiful? While this may be true for math, we have to remember that a lot of your math has seen pertinent applications in computer science, and that's important to security in today's world. Professor Chandrasekhar Khare and his panel chose Professor Sabyasachi Mukherjee from TIFR Bombay as the winner of the Infosys Prize in Life Sciences, and I would request him to come here and tell us more about his work.
All right, good afternoon. Thanks, Vamna, for the introduction. And thanks to the Infosys Science Foundation for this honor. Right, so in my 12 minutes and 49 seconds, I'll try to give you a quick glimpse of the kind of math I do. And yeah, good thing Vamna actually mentioned that math can be abstract. Math can definitely be abstract, and part of math's job is to be abstract and give concrete formal proofs to things that are observed in nature. However, the kind of things I work on, namely dynamical systems, which, by the way, did show up in Sushant's talk a little bit. So it actually comes from physics. And the message that I want to basically convey to you is that a mathematician working on these sort of applied-ish areas of mathematics need to be alert, need to keep their eyes open, look at questions that arise in physics, biology, and things like that, and then draw inspirations to try and justify the observations. All right, so what is a dynamical system? A dynamical system is just anything that changes over time. It could be a planetary system. It could be, this planetary system where you have a sun and you have the planets revolving around it. It could be a population of fish, could be a population of anything else, could be the weather, could be fluid, gas. Here, this shows like a red smoke coming out of the wings of an airplane and creating a vortex for turbulence and things like that. You would like to understand what kind of dynamics it creates. And you want to understand how the system is evolving, what is happening in the long run. Is it stable? What does it even mean to be stable? To do any kind of mathematical justice to any of these questions, people will first have to model these things mathematically. Now, I'm not going to tell you how to model anything mathematically, but yeah, there are a few ways of doing it. For instance, the most common one, I guess, is that many of you here are familiar with are differential equations. So what would be a differential equation to someone who has never seen it? It's basically a way of predicting small changes in time. You have something that's changing over time, and you want to prescribe how the system changes just a little bit later, like in 10 to the negative 10 seconds or something. And then the key point is that trajectories can be extremely wild. So here I have a differential equation, or rather the motion of a particle, which is just going round and round and round and creating what's called a strange attractor, or a butterfly. That's another example of a wild trajectory. And when you have such wild trajectories, it's extremely difficult to be precise to say exactly what's going to happen to the motion of a particle or to the system in the long run. There's another way called iteration theory. This is basically kind of a picture that Sushant showed in his slide. Here what you're saying is, instead of trying to understand the motion continuously, I'm going to take snapshots. I'm going to take snapshots every minute. And I start with whatever these things mean. X is my system. F is just a rule. It's just a rule that's telling you how the system changes from moment time 1 to time 2, and then from time 2 to time 3, and so on. And you want to understand what happens if I keep hitting this button again and again and again a billion times. So I'll give you a mathematical example. So far, there has been no math, just to prove that I do a little bit of math. So what's happening over here? I'm trying to do something that people have been doing in school, right? You want to solve polynomial equations. You have a polynomial, you want to know where it vanishes. So where does the polynomial x cubed minus 1 vanishes? Well, with a little bit of math, you can easily find it out. But Newton had an idea of solving the roots of a polynomial using some kind of a dynamical method. So his idea, and I'm not going to tell you what exactly he did, but he came up with a strategy. You start with a point, and you apply whatever this Newton method is called, and you keep doing it again and again and again, and with some luck, the point is basically going to converge
towards a root. This is basically what Sushant showed. You start with some sort of a solution and you go and keep hitting this button again and again and try to go towards the maximum flow. So you want to do something, you want to get somewhere, but you don't know how to get there in one step. So you do an approximation, you do again and again and again and again, and hope to go towards the solution. Now, what this picture is showing you is something quite bizarre. So it happens that there are 3 solutions of this equation. These are displayed by the 3 dots. And one is in the red region, one is in a green region, the other is in the blue region. And in this picture, you have tiny blue and red and green islands, infinitely many of them. And no matter which green island you start off with, if you keep hitting your button, you'll go towards the green solution over there, the green root. Whichever red island you start off with, eventually you're going to go there, and whichever blue island you start off with, under iteration, eventually you're going to go to the last one. So what's cool is that there's a very sensitive dependence on the starting point. You can start with a red point, maybe somewhere here, and if you keep hitting your button, you'll go towards the red point there, but there is a blue point very close to it, like maybe the first 10 decimal digits are the same, but the 12th decimal digit is slightly different, and then so for the small perturbation, small change initially, but you keep hitting your button again and again and again, all the mistakes accumulate, and eventually you're going to see something completely different long-term behavior. Small change becoming some huge mistake at the end of the day, or completely giving rise to different behavior. This is what chaos means. Then there is I only have to talk about this because this is related to the kind of math I do. There are other ways of modeling dynamical systems when a system does not necessarily have a unique way of evolving. There could be like multiple ways of going from time 0 to time 1. These things are called group actions. So there are many different rules to go from time 0 to time 1. For instance, you can think of 3 mirrors over here. You have some sort of a disk, and you have a green mirror, and a red mirror, and a blue mirror. And you can take a point, and you reflect it either in the green mirror, or in the red mirror, or in the blue mirror. And if you keep doing that, you're basically going to see this checkerboard pattern of the whole disk, depending on which mirror you're constantly reflecting by. That's just an artistic impression of this phenomena. Now, as I said, in dynamical systems, the general goal, no matter what your initial problem is, no matter what you're trying to solve, no matter what the source of the problem is, you always want to understand the long-term behavior of these trajectories of the evolving system. And you want to understand how stable these trajectories are. And this takes me back to this example. This is what I meant by stability. You take a red point, eventually you're going to go there. You take a small perturbation, start with the blue point right here, and you go over there. So there is no stability. Slight perturbation gives rise to very different end behavior. So you want to understand the sort of stability or the lack of it. And finally, what happens if the rule is slightly altered? These are some general goals in dynamical system, but the key point is that the answers would typically depend on the systems. There are many, many dynamical systems. Each of them exhibits some special kind of dynamical behavior. Everything depends on exactly what the system is. However, there's a specific situation that I work on in conformal dynamics, I'll tell you what that is, where different dynamical systems give rise to similar chaos. So I was talking about this iteration theory where you describe how to go from time 0 to time 1 and from time 1 to time 2 and so on. And I'm on just a real two-dimensional situation right now. And in the real two-dimensional situation, there are 3 very simple ways of changing things. Just reflecting, rotating, and scaling. Scaling just means make something bigger. And a conformal map is something that locally looks like that. The map does not exactly look like these 3 easy, simple things, but locally, whatever that means, they look like either a reflection or a rotation or a scaling. But this actually gives rise to a large, rich class of transformation rules. For instance, you can just take a polynomial and keep iterating it. Every polynomial is an example of such a transformation, or you can just do reflection, like you have red 4 mirrors here, and you keep reflecting in these mirrors. This is an example of the chaotic set, this weird fractal-looking set, the boundary of that fat ant. This boundary is a very weird fractal-looking set, but this is exactly the region where the dynamics is chaotic. Same thing over here, the black thing is the region where the dynamics is chaotic. These two dynamical systems came from completely different perspectives, completely different transformation rules, nothing in common to begin with. However, these guys look similar. There are more examples, more pictures where, once again, the things on the top, they came from these sort of multiple rules, whereas the objects on the bottom, they came from a single transformation rule. So very different dynamical systems, but giving rise to very similar chaotic behavior at this end of the day. About 100 years back, Fatou was the first person who sort of noticed this without drawing any pictures. God knows how he actually came up with this. He thought that maybe there's a general umbrella to study these things under the same framework. About 45 years back, a great mathematician called Sullivan managed to show that at least in some cases, one can indeed take a piece of technique from one world and apply it to study the other kind of object. And maybe there are some philosophical analogies between them. So this is something I have been working on. So this is like a dictionary. You have two different kinds of dynamical systems. They are very different to start off with, but there's a similarity in their long-term behavior when you keep hitting your button again and again and again. And this dictionary is not exactly a translation, because the objects are so different, you can't really translate a word here to a word over there. But there's some rough analogy. And the job of the dictionary is to make this analogy more precise. So this is what I have been working on for the last, several years. What we can prove is that, so at the moment, obviously I'm not going to tell you any precise statement of a theorem, but what these pictures show you is that in many, many situations, dynamical systems are chaos. All these fractals are basically the chaotic sets, the sets where the dynamics is chaotic. And these chaotic sets coming from two different worlds of dynamics, two different kinds of dynamical systems, not only look similar, but we have a complete understanding of why they look similar. Looking similar is one thing, but a mathematician wants to understand, so looking similar is like just aesthetics. When you look at a picture of a fractal, you just look at the picture of the fractal, it looks beautiful, and then you forget about it. But a mathematician wants to understand why they look similar. Is there a similarity between the chaos between these two, displayed by these two systems? And we have a complete understanding of why these systems actually look similar, how their chaos are related. And once you understand this, it's a bit like, I was telling someone else today, it's a bit like DJing. You have some classical music, you have some contemporary music, you want to find how they're similar, you want to find out how the beats are similar. If you can't find similarities, then you want to fuse them, construct something richer and nicer. So that's what we did. Once we found similarities between these objects, we found their commonalities between them, then we managed to fuse them together, giving, and this is basically related to Fatou's initial dream of this general umbrella, but once we have this kind of a way of fusing very different dynamical systems under a common umbrella, we are looking at some sort of a realization of Fatou's initial dream, which was 100 years ago. Fatou said that there should be a general theory of studying these different kinds of dynamical systems, and this is the first evidence of that. One more, where basically what the picture is showing you is you have some sort of a complicated dynamical plane here, and the inside, the dynamics is like a reflection, like a kaleidoscope, and outside, what you're seeing is some sort of a polynomial dynamics, which are very different objects. And once you develop such tools, obviously, good math gives rise to applications to other areas. So there are tons of applications to complex analysis, real algebraic geometry, Teichmüller theory, including probability and random matrix theory, and so on, which I'll not bore you with. So thank you for listening.
Thank you so much. And I'm sure we have a lot of questions for you. Beginning, though, did you raise your hand? Sorry. At the back, someone at the back. You did raise your hand. Sorry. Can we have a mic here?
In classical mechanics, like the examples you showed, in an inherently unstable system, the starting point, it differs a little bit. You go into different, you get attracted to different points. But nature is not classical. So inherently, if you is there a mathematics which says, okay, I'll start with my point, but it's actually itself a probability distribution? So in which case, I don't know, does it go to 3 different points in some proportions?
Okay, I lost my slide somehow. Did I? Maybe. Yeah, so basically there's a region where the dynamics is not chaotic, where you know with full certainty where you are going to go. Small perturbation does not make a difference. Then there is a region where small perturbation makes a difference. For instance, well, all of these fractal-like objects, if you're right on that thing, then you don't know, because small perturbation can take you here or there. So instead of studying what exactly is happening to a single point, one does put a probability distribution measure in mathematical terms, well, let's say a probability distribution on that fractal set itself, and wants to understand long-term equidistribution properties, namely long-term behavior of points or trajectories with respect to these nice probability distributions. So you want to understand the dynamics of points on that fractals probabilistically. That's exactly what people do. That's also done in ergodic theory.
So I don't fully understand the duality, obviously, but on one side you have iterations and the kind of things you get from numerics. On the other side you have symmetries. So one side is sort of dirty, the other side is very pretty. And I assume that there are ways to find statements about the iterative part by using things on the other side. Have I grasped that correctly?
That's roughly right. But when you say one side is, so for instance, this side is obtained by symmetries, but you have many symmetries. The other side is a single transformation, which is not so pretty, because it's like solving that Newton equation where you have high degree and problematic things. So this guy is not nice because it has a complicated formula. You don't see geometry, but there's only one bad guy over here. Here, you have many nice guys, but these nice guys are fighting against each other, which is what giving rise to chaos. So to find a statement that's common to these two different worlds, you have to somehow make them meet halfway. And there are 2 ways of doing it. Either you try to cook up one bad guy from these many nice guys, and that's exactly what we do.
Okay, thank you.
Thanks, Mr. This was very, very interesting. Just trying to understand, so without giving a formal statement, are we able to say something like that on the right side, can you identify sort of these symmetries that look a little crooked, and with some minor transformations, they actually capture the topology appearing on the right-hand side?
So let me try to understand. Okay, first thing is the fractals you see on the left are homeomorphic to the fractals on the right. So they are exactly the same shapes.
Okay.
And what's your exact question?
Right. So does that mean the way, like, let's just take the first picture. You have 4 really nice mirrors on the left-hand side. Are there perturbed mirrors on the right-hand side which would generate the fractal?
Great. Thank you. That's a great question. Yes. So here I have 4 nice guys, namely 4 reflections in nice mirrors. I have to patch them together to construct a weird kind of mirror over here, which should sort of look like that, but now the mirror is not your round mirror, but some complicated mirror that you see in a museum, in a science museum, let's say. So that's the idea, yes.
Thank you. And if we have no further questions right now, you can, if you think of any, please catch Sabyasachi over tea. Thank you so much. The Infosys Prize 2025 in Physical Sciences is awarded to Professor Kartish Mantiram from Caltech for his pioneering work on sustainable electrochemical routes to essential chemicals. His work seems like magic, making fertilizer out of thin air. In our brochure, in our beautiful brochure which is on your table, you will see the technical citation by jury chair Professor Srinivas Kulkarni and a beautifully simplified explanation of his not-so-simple work. He demonstrates how renewable electricity can drive selective efficient synthesis of chemicals that are fundamental to agriculture and industry. To tell you more about the implications of his work, I invite Professor Mukherjee to stage. Sorry, Professor Kartish Mantiram.
All right, thank you, Bhavna, for the kind introduction. I want to start by putting up this image and asking us to think about where the carbon footprint is. And we might instinctively point to the gasoline-powered vehicles or to the electricity powering the lights, but we know all too well that there is a carbon footprint behind everything that we see here. That there's a carbon footprint behind the steel of the flagpole, behind the cement of the buildings, behind the plastic of the billboards, behind the clothing that everyone's wearing, even behind the food that's served at a restaurant like McDonald's. So these carbon footprints are literally in everything that we are standing on, holding, wearing, eating, and using throughout the day. And it is essential that we find ways of eliminating this carbon footprint. So this plot shows the carbon footprint of the top 18 commodity chemicals as a function of their production volume. And you'll see immediately that there is one chemical, ammonia, all the way at the top there, that it has its own y-axis. And it needs its own y-axis because the carbon footprint of ammonia is so large that if you had plotted everything on a single y-axis, ammonia would be up top and everything else would be compressed down in the bottom half of the plot. So if we're serious about decarbonizing chemical manufacturing, we absolutely have to do something about ammonia. And if we want to achieve deep decarbonization of chemical manufacturing, then we also have to do something about all the other chemicals that are shown here. We have to do something about ethylene, propylene, BTX, methanol, ethylene oxide. This is a challenge because today we make the world through a petroleum-based supply chain. We start with a barrel of oil, and we've come up with all these clever tricks to be able to make everything that we need. And it's the vision of my group to develop an alternate paradigm, one where we start with air and water and can convert those to make the chemicals that the world needs. So imagine if you could take nitrogen, CO2, and water, 3 molecules that give us a source of 4 elements, carbon, hydrogen, oxygen, and nitrogen. Imagine we could stitch those together through the action of electrified catalysts. These are nanomaterials and proteins that can orchestrate a molecular level dance through which you can make the products that the world needs to sustain our quality of life. That's what we're working on. There are 2 examples that we'll talk about today. The first is making ammonia, which is used as a fertilizer. And the second is on making epoxides. Epoxides are hidden heroes of the chemical world, something that I'll hope I can make that point to you in the second half of what I have to share today. But we'll start first with making ammonia. So we make ammonia today using a process called the Haber-Bosch process. This is a reaction where we start with methane and water. We convert those all the way to hydrogen. And in the process of ripping hydrogens off of carbons and hydrogens off of water, the carbons and oxygens come together, and we make CO2 as a stoichiometric byproduct of this reaction. We then take that hydrogen, and we react it with nitrogen to make ammonia, 400 to 500 degrees centigrade and 200 to 250 atmospheres of pressure. Now, the 2 major problems here are, first, we have an enormous CO2 footprint that arises from this process, the largest of any chemical that we make today. And on top of that, we have relatively harsh conditions, greater than 700 C and 200 to 250 atmospheres of pressure. These harsh conditions require centralized manufacturing. You can't make ammonia close to where it's needed because the conditions are so dangerous. You have to do it in really large, centralized chemical plants like the one that I'm showing here in Germany. So that's our wish list then. A next-generation method for making ammonia should, 1, eliminate the carbon footprint, and 2, it should operate at more mild conditions that are conducive to distributed manufacturing. So this is our vision. Imagine you could start with water, break it down to make hydrogen and oxygen, that you could then take that hydrogen, react with N2 to make ammonia. At 25 degrees centigrade, atmospheric or near atmospheric pressures, driven by renewable power instead of the temperature and pressure that is used today in the Haber-Bosch process. If you did this, you would eliminate the carbon footprint. There's no input of hydrocarbons, and there's no stoichiometric CO2 being generated either. And by operating at more mild conditions, you could make that ammonia closer to where it's needed. So imagine then that you have a solar farm. It's generating abundant renewable power. You can feed it to a small local device, one which breathes air, takes water from a neighboring source, makes it into ammonia that you can then feed to a neighboring field. This would be a very different way of making the ammonia that we need today as a fertilizer. So the main challenge in doing this is that we need catalysts that can facilitate breaking the right bonds and forming the right bonds. And here you'll see a schematic that demonstrates the approach that my group has taken, and starting in 2017, one where first we plate lithium ions to make lithium metal on the surface of the electrode. This lithium metal is really special. It has the ability, when it encounters a molecule of nitrogen, to break that nitrogen triple bond. It makes a solid-state, dissociated form of nitrogen, which is now ready to accept a proton. So you can see this proton here coming from hydrogen oxidation at the anode. That in turn reacts here. You discharge lithium ions, replacing them with protons. You make ammonia, which comes off. And the lithium ions that come off, you can now recycle and plate again. So you're not consuming any lithium in the process. That's what makes it a catalyst. So ammonia is then made as a product. And what we found in our earliest studies in 2017 is that the slowest step of this process was not the interfacial reaction. It wasn't the reaction of nitrogen with lithium. It was the journey of lithium from a bubble to the surface of the electrode. That was the slowest step, a transport process, one that involves diffusion and convection. So that was a scientific insight that we had, but we then took this a step further to actually solve it. We developed a new approach of introducing nitrogen gas to this reactor, one that uses a gas diffusion electrode. This is a porous medium in which you can contact the liquid phase electrolyte with the gas phase reagent that you're bringing in. This allows you then to shorten the distance over which the nitrogen needs to travel, and you can then accelerate the rates of nitrogen fixation. This immediately led to an order of magnitude improvement in rates, and that in turn, in the broader literature, this approach has now been adopted, and other groups have taken it by another order of magnitude. So this architecture now is one that is being adopted worldwide. So as we're starting to look at this process through a more practical lens, one thing that we're thinking about now is the cost of lithium. This lithium, of course, is now being used for lithium-ion batteries, for which there is skyrocketing demand. So we need to find now cheaper ways of doing this process. This has motivated my group to look at the use of sodium instead. But the problem with sodium, and why so many told us that it would not be possible, is that sodium lacks the intrinsic reactivity with nitrogen that lithium has. And so this means that we can't rely on sodium alone. And this is why my group has now introduced the use of titanium, a partner for sodium, that they can work together to drive this fixation reaction. Sodium providing the driving force, and titanium actually breaking the nitrogen triple bond. So you'll see here, we have a 10x reduction in cost just by doing this alone. That's how much cheaper the combination of sodium and titanium are relative to lithium. And you'll see on this plot here just how far we've come in the last year. Production rate on the x-axis, energy efficiency on the y-axis. The point sizes indicate pressure, so smaller points at 1 atmosphere going up to 20 atmosphere. All those pressures are an order of magnitude less than what the Haber-Bosch process requires, so these are relatively low pressures. In gray, we have lithium. In pink, we have beyond lithium. So even though the lithium-based systems have had a head start of many years now, for the beyond lithium systems that we've introduced in just the last year, you'll see that we're already approaching this frontier denoted by the dotted line. So it's really interesting to see how a possible future in which ammonia production is not just more sustainable, but possibly cheaper could be upon us. So we'll shift gears now to talk about making epoxides. So I mentioned earlier that epoxides are these hidden heroes of the chemical world. They are literally in everything that we are using throughout the day. So if you drink water out of a plastic water bottle today, it was probably made of polyethylene terephthalate. That's derived from epoxides. The seat cushions that you're all sitting on, the squishiness of it, probably comes from a polyurethane foam. So epoxides are part of that seat as well. So you're going to constantly use epoxides throughout the day without even really knowing that they are there. Here I'm showing the different ways in which we make epoxides. You can do, for instance, a direct oxidation process. That's the first that I'm showing here. converting ethylene with oxygen to make ethylene oxide, 280 degrees C, 30 bar of pressure. If this was all that happened, I would have no qualms with this reaction at all. But the problem is that when you introduce oxygen with a hydrocarbon, you also over-oxidize. You go all the way to CO2. And so this is in part why ethylene oxide production has the 5th largest carbon footprint of any chemical that we make today. Recognizing this, alternative processes have been devised. I'm showing here the chlorohydrin process. Take an olefin, react with chlorine and water, make a chlorohydrin. You then treat with base. It closes the ring. You make an epoxide, but you also make a stoichiometric calcium chloride side product. And that may seem innocent, but this gets discharged into rivers, into streams, into oceans. You also have organohalide side products, which are extremely harmful to human health. And the world has stopped issuing permits for this process. There is no country in the world today that's issuing permits for the chlorohydrin process, given these environmental and human health harms. And that's where the peroxide process comes in today. Here, reacting an olefin with hydrogen peroxide, 50 to 90 C, 10 to 15 bar, making propylene oxide, just water as a byproduct. This is a beautifully clean reaction. But the problem is explosiveness. You take a hydrocarbon like propylene, you put it together with hydrogen peroxide. That is a day that my friends who work in the chemical industry tell me that you are afraid to go to work, right? Because there are explosions that happen routinely at these chemical plants, an average of 1 fatality a year, right? So these are significant problems. You're picking your poison today, either a carbon footprint, an environmental discharge, or explosiveness. And that's what motivated my group to develop this process, one where an olefin can be reacted with water. Water is the oxygen atom source. You make the epoxide, and you co-produce hydrogen, which is a valuable side product to make. This is the electrified platform that we developed, one where you're starting with water, breaking it down, transferring that O atom to the olefin, making an epoxide. Protons are liberated, electrons go through the external circuit, protons come across here, electrons there, and you make hydrogen at the cathode, right? So that's an electrified process for doing this. Historically in the literature, palladium and platinum-based systems have been explored, either purely palladium or purely platinum. And you can see here they don't work very well. Low selectivities, low production rates. And we introduced in 2024 an alloy of palladium and platinum, which far outperforms in terms of rates and also starts to push selectivities. And very recently, just last year, we've now discovered Earth-abundant compositions, ones based on cobalt, that are dramatically cheaper. So this, in turn, will allow us to actually achieve the techno-economic goals that we have for this process, right? This takes us even closer to trying to bring this technology out into the real world. So I've talked about ammonia. I've talked about making epoxides. As you might guess, this is just a small part of what's needed to decarbonize the physical world. We have to electrify hydroformylation, carboxylation, and countless other chemical reactions. And that's where it's going to take a huge community, right? I hope for people in this room, for people beyond this room in the broader scientific community, it's going to take brilliant minds everywhere working together if we're going to actually decarbonize the physical world. So with that, I'd like to thank our students and postdocs. One of them came in one day and said, you know, I think we're chefs of the molecular world, and I take everything seriously. So I went and I bought chef's hats and brought all these props in the next day, and they all kind of looked at me like, did you really take it this seriously? But we took this photo. I think it shows just while working as hard as they do and with the vision and creativity that they do, they also know how to have a bit of fun. I'd also like to thank the Infosys founders for their conviction in the power of science to transform society. I think it's really incredible, especially in this time that we live in, to be able to look to that and see that belief. The dynamic team at the Infosys Science Foundation, who have taken care of every last detail to bring us here together today, so we're extraordinarily grateful for that. And finally, my family, my parents, Arumuga Manthiram and Rajeshwari Manthiram, who are here in the front. Without their hard work and determination, there is no way that I would be on this stage today. They believed that their lives with their kids through their hard work could be better, and I'm eternally grateful for that. To my wife, Amrita Saigal, who's also here in the front, Amrita has taught me how to have fun on this adventure that we call life, and for that I'm grateful. Our daughters, Avni and Mira, who are here, you'll see them running around at high tea probably. You'll know it when you see them. It'll be loud and joyful and laughter everywhere. So they've infused tremendous joy in my life, so I'm very thankful to them as well. And to all of you for coming out. So thank you, and I'd be happy to take any questions.
Thank you, Kartish. Your energy is infectious. I'm sure we'll have a lot of questions. And this, go ahead.
With respect to the production of ammonia for fertilizer, how would you would you like to comment on the value of engineering rhizobia to do it more broadly for all plants versus your electrolytic process, even with the sodium and titanium?
Yes, absolutely. So at present, if you look at where nitrogen originates from, if you look at any meal that we have and you trace back the origins of the nitrogens that are contained in there, half are of synthetic origin, the Haber-Bosch process, and half actually come from nature, right? Bacteria working hard in the soil to actually break down nitrogen, make ammonia, a beautiful symbiotic relationship that the bacteria have with the plants. What's really neat, and this is what I love about science, right? We're each taking bets on something. We believe in something and we take a bet. But the beautiful thing is that for what you just described, there are groups that are taking that bet, right? This belief that if we can engineer bacteria to be able to better fix nitrogen, if we can supercharge them with basically giving them food stores and encapsulated granules, right? The work of people like Chris Voigt and others that are really driving this forward, that's possible. And so I think that there's something there. It's not the horse that I picked, but I do think that there's more room for more than one solution to drive us all towards this sustainable future.
Thank you.
So to follow up on that question, living systems do these things at ambient temperature and pressure using some other strategy than the one you're proposing. And so it has to do with specificity and shapes and really bringing the atoms together at the nanoscale. Could you just not use the living systems but apply those principles in large, scalable, synthetic ways?
Yeah, so we take a lot of time to actually look at how nature does this, and I think we've learned a lot from the enzyme nitrogenase. My group actually works with it now. We're working on finding ways of electrifying nitrogenase. So imagine you could take it, put it on an electrode, and actually start to drive this chemical process. Now, the challenges that we run into are twofold. One, nature has developed this process such that it delivers nitrogen, or ammonia rather, at the flux that is needed for this symbiotic relationship. When you try to push it harder, there are all sorts of regulatory mechanisms that come into place that actually make it difficult. There's also a sacrificial amount of hydrogen that's evolved in that process, on top of which it natively also uses ATP. So you have to generate all this native energy currency. But that is to say that those are the problems to be solved to make that approach work. I do think that there's something there, just it's not yet in a place where the rates or the techno-economics are close to the metal-mediated methods that I described. Yet the science should absolutely be done there to make it work.
So, Karthik? Hi, just thank you, very fascinating talk. So just to push this further, how far do you think are we from deploying these solutions to replace the Haber-Bosch process? Can you identify the major challenges and maybe how much more improvement we need in terms of the techno-efficiency of these processes today?
Yes, I've come to realize that commercializing something is deeply philosophical. It's a decision you have to make when something that you've worked on in the laboratory within a relatively safe space is actually ready to see the world, right? To be subjected to not the intellectual pressures that we put our science under, but under the pressures of investors and VCs who want to see things happen fast, right? And so there are others who would say that this should have already been pushed out of the lab, right? There are people who have that philosophical conviction. I am someone personally who likes to de-risk. So the day that this leaves the lab, I know that it's going to work, right? And so that is to say that if we had already commercialized this, I think the roadmap would have changed time and time again. And now what we're seeing, even in the last few months, is that the roadmap has taken a significant shift with introducing sodium into the game. So I think that we are now a matter of years from this being something that can be spun out, but I think it's close. It's getting closer. I used to say it's 30 years away. Now I think it's just a few years away.
Thank you. We have time for one last question, right at the back.
Hi, can you hear me?
Yes, yeah. I can.
Great. You mentioned that the chemicals process has overlap with some, tech considerations, including price volatility for lithium, that drove some of your cost considerations. I took the liberty of looking up the kind of 5-year prices, and it does look like lithium has kind of dropped since its peak high. And in the meantime, titanium has at times been higher than lithium. So I realize that it's low-ish now, but it seems like both of those elements, those substances, have significant volatility. So would you say that in planning your work, do you take a bet? How do you forecast and kind of how do you decide given the volatility of both substances?
Yeah, it's constantly evolving. And the best thing to do in that circumstance is to develop a flexible process, right? One where the same architecture, the same electrodes, the same flow systems can be swapped out, right? And so the good news is that the process that involves lithium versus that of sodium and titanium, it works in the exact same architecture. So in our group, we have a single architecture, but that is flexible to work across these metals and metal combinations. And so that, like you said, it's a moving target, right? What is cheap today could be expensive tomorrow. If we start to use materials for this process, maybe it becomes expensive because we are also now increasing demand for these metals, right? So it absolutely is a moving target and something that I think the only philosophical way to solve that is by engineering flexibility into the platform from the outset.
So I think with that, we're going to wrap up right now, unless someone has a last question.
So I had a question about scalability. How scalable are your processes?
Yeah, so one of the cautions that we should take at the outset is that thermochemical processes, like the Haber-Bosch process, they're done in volumetric reactors. And that means that they scale as R cubed. As you make them bigger, you actually get immense gains. This is a significant difference with electrochemistry, where the processes tend to scale with a square exponent, right, to the second power, because they're area-based processes. Now, the advantage we have is that because they scale in that way, they actually make really good modular systems, right? This is exactly the playbook that we have with lithium-ion batteries, right? That you can make modules and stack them up, and you number up to scale up, right? That's very different from the history of Haber-Bosch. So that's the same thing we have to do here. If we're going to scale this up, we have to number up, right? Make a really cheap way of making each model, whether that's like 18650 cells that are the heroes of the lithium-ion battery world, right? Or pouch cells that are now coming more into vogue. You have to make that one unit and number it up by making many of them. And that's what's going to be needed for this process in order to scale it up.
Yeah. Anyway, the last comment is, I thought we didn't have a CO2 problem.
Depends on who you talk to, but I'm glad to be here today where I think we all believe that it is, I hope.
Yes, I love that. I think we're more or less on the same page. Thank you, Kartish. Thank you so much. I love that we were able to fill up a room for an academic and an interdisciplinary event, but nonetheless, thank you so much for coming. We love the energy. So let's catch our winners of a tea outside. Thank you all for coming. Thank you. Oh yes, and please, you are all invited to the Infosys Prize ceremony tomorrow at 5:15 p.m. Thank you.